In this component, we'll summarise the Rankine-Hugoniot relations, and we'll have a look at how properties of a gas change across a normal shock wave for some typical conditions. Let's just set the scene again. We're looking at the flow of a calorically perfect gas as it passes through a normal shock wave. So the gas starts at condition 1, Mach number M1, static pressure P1, static density ρ1 and static temperature T1. Immediately behind the shock, each of these properties of the gas change, and we denote the conditions as state 2, so M2, P2, ρ2 and T2. At the end of the last component, we'd found an expression for the density ratio across a normal shock wave in the form of ρ1 over ρ2. We'll present the ratios here as the value of a quantity downstream of the shock wave over the value upstream. So the expression for ρ2 over ρ1 is just the inverse of that for ρ1 over ρ2 from our last component. This is the expression. This shows that the density ratio just depends on the Mach number of the flow upstream of the shock wave, M1, and the ratio of the specific heats of the gas, gamma. So for a given value of gamma, we can plot how the density increases across a shock wave. This plot shows the density ratio vertically and the Mach number on the horizontal axis. I've plotted the results here for Mach numbers ranging from 1 to 10. This plot is for gamma equals 1.4. This is the value of the ratio of specific heats for air. Gases composed of diatomic molecules have gammas of 1.4. And since air is composed primarily of nitrogen and oxygen molecules, which are both diatomic, then air has a gamma of 1.4. We see that the density ratio across a normal shock wave increases rapidly with Mach number initially, and then the rate of increase slows down at higher Mach numbers. In fact, the density ratio asymptotes to a constant value for very high hypersonic Mach numbers. Richard Morgan will discuss further what happens as the Mach number becomes higher in section 5 of the course. Let's see what happens to the pressure ratio across a shock wave. The results we obtained by completing the analysis in the last component is this. To get this, we had to do some manipulation of the equations we'd developed. As for the density ratio, the pressure ratio depends only on the Mach number upstream of the shock wave, M1, and the ratio of specific heats, gamma. And when we plot the pressure ratio across a normal shock wave as a function of Mach number for gamma equals 1.4, we obtain this result. The ratio starts at 1 for a Mach number of 1. You can't really see that clearly in this plot. And the reason it's not clear is because the vertical scale is so large. Note that we're plotting the pressure ratio over a range from 0 to 140 here. And this brings out the first important thing to note. You can see that the pressure ratio just continues to increase as the Mach number increases. And the rate at which it increases with Mach number just continues to get higher. So the pressure ratio across a normal shock wave gets very large at high Mach numbers. So how about the change in temperature ratio across a normal shock wave? This is the expression we obtain for the temperature ratio. This one is starting to look a little complicated. But again, the ratio just depends on the Mach number upstream of the shock wave and the ratio of specific heats. When we plot this, we see that the ratio starts from 1 at Mach 1. And, as we saw for the pressure ratio across a normal shock wave, the temperature just continues to increase with increasing Mach number. And the rate of increase gets larger as the Mach number goes up. So this indicates that temperatures downstream of a normal shock wave can become very large at high Mach numbers. Before we go any further, I must point out that these results are for the case of a calorically perfect gas. In reality, as we get up to high Mach numbers, unless we're starting at really low temperatures upstream of the shock, the temperature of the gas will become important, and our assumption of a calorically perfect gas will not be valid. These real gas effects would lead to lower temperature ratios than would be indicated from this plot at the high Mach numbers, as some of the energy from the flow would be absorbed in exciting molecular motion and possibly breaking the bonds between molecules in the gas. Again, we'll have more on this in section 5 of the course. So looking back at our plot, we can see that the vertical scale here goes from 0 to 25. This is smaller than we saw for the pressure ratio. Recall that our scale was from 0 to 140 on the last slide. So the temperature ratio is lower than the pressure ratio across a normal shock wave, but we still get some pretty large temperature increases at the hypersonic Mach numbers. So the Mach number downstream of the shock will be m2, and the Mach number is the speed of the flow divided by the speed of sound. So m2 is equal to v2 over a2, where v2 is the speed of the flow and a2 is the speed of sound. Let's expand that by multiplying top and bottom of the equation by v1 times a1. Might seem like a strange thing to do, but you'll soon see why. In doing this, we have three ratios: v2 over v1, v1 over a1, and a1 over a2. Let's look at each of those in turn. Recall from our analysis of normal shock waves that the conservation of mass gives us that ρ1 times v1 is equal to ρ2 times v2. So v2 over v1 just equals ρ1 over ρ2. Let's put that in for our first ratio. Now, v1 over a1 will be the Mach number upstream of the shock wave, so it'll be m1. So the second ratio just becomes m1. Finally, recall that the speed of sound is the square root of gamma times r times t. Therefore, the third ratio, a1 over a2, will become the square root of gamma rt1 over gamma rt2. But if we have constant specific heats, gamma and r are the same upstream and downstream of the shock wave. So they cancel, and we're just left with the square root of T1 over T2. We put this in for our expression for A1 over A2, and we have M2 in terms of the Mach number upstream of the shock wave and the density ratio and temperature ratio across the shock. But now we have expressions for both the density ratio and the temperature ratio. So we can put those in and get an expression for the Mach number downstream of a normal shock wave. And here it is. Now, not surprisingly, the Mach number downstream of the shock depends only on M1 and gamma, just as we had for the ratios of various other properties across a shock. We can plot M2 as a function of M1 for a gamma of 1.4. Here, the vertical scale is ranging from 0 to 1.2, and M1 is again ranging from 1 to 10. The first important point to note is that the Mach number is always subsonic downstream of a normal shock wave. This will be the case whenever gamma is greater than 1. You can see that the Mach number downstream of a normal shock wave drops rapidly at first as the Mach number increases, but when we get to hypersonic Mach numbers, above Mach 5, the Mach number downstream of the shock is around 0.4. At very high Mach numbers, for a calorically perfect gas, the Mach number downstream of the shock asymptotes to a constant value. For gamma equals 1.4, this value is just under 0.38. You saw that some of the expressions for the ratios of properties across shock waves get a little complicated. Just as you saw with Vince when looking at isentropic flows, you'll be able to find tables of data for the changes in properties across normal shock waves. These are usually presented as a function of the Mach number upstream of the shock wave for a given value of gamma, usually for gamma equals 1.4. NACA report 1135 is a good example of where you can find some normal shock tables for gamma equals 1.4. You'll also find some good calculators for finding how conditions change across normal shock waves. A good one is the Virginia Tech Compressible Aerodynamic Calculator by William Davenport. A good calculator such as this one makes calculations with different gammas easier. In the next unit, we'll look at the losses associated with shock waves. This will lead us into looking at how the total pressure and the entropy of a gas change as it's processed through a normal shock wave.